Okay, so right now we're going to begin chapter 3. Okay, so come on in, settle down. Okay, so chapter 3 is all about numeric summaries. Numeric summaries for numeric data. Okay. So again, just putting this into the context of everything in statistics, we don't study the population, we study a sample. We're hoping that we can, by observing the sample, we can make conclusions that apply to the population. When we look at the sample, and in this case when we're looking at a sample with numeric data, we want to be able to describe what our sample looks like. We want to be able to describe that sample without having to mention every single individual. And so we've talked about graphic displays of numeric data just before the break, which included a histogram and a dot plot, and later on we'll also talk about the box plot. So we have ways to describe numeric data with it graphically, and chapter 3 is about describing that or summarizing that numeric data with numeric summaries. Okay, and this is something that you guys are already familiar with. Okay, so for example, many of you are concerned about your GPA, your grade point average. Okay, so as you go through school and you take classes, at the end of your class you get a grade, and that grade is turned into a number. So you get an A that's worth 4 points. Okay, you get a B, it's worth 3 points, or something along those lines. Okay, and then your GPA, I'm assuming it's weighted by how many credits your courses are worth, right? So the hard classes that are worth a lot, they count more towards your GPA, and the credit classes that were easy, they count a little bit less, or things like that. It's like this weighted average. And this GPA is supposed to summarize your entire academic career with a single number. Okay? And so if somebody says, oh, I'm a 4.0 student, it gives you an idea of what kind of student that is. Somebody says I'm a 3.9, it also gives you an idea of what kind of student that is. If someone says my GPA is 2.2, it also gives you an idea of, you know, what kind of student that person is. Okay, and there is a great danger in trying to boil everything down to a single number. Okay, it's useful. GPAs are useful, but there's also there's a great flaw in that a single number can't capture all the information that there is. Okay, but it's useful in comparing. Okay, and so you know that the 3.9 and the 4.0 student have done well in their classes. We don't know which classes they've taken, but we know that they've done well in the classes. And compared to a student with a 2.2 average, we can generally say that for the most part, probably the student with a 3.9 or 4.0 is probably a better student than the student with a 2.2 average. Okay? Now, of course, that's not definitive, because there could be all sorts of nuances and other things going on behind that number. But for the most part, on average, if you randomly select a 4.0 student and you randomly select a student with a 2.2 average, typically, most of the time, the student that you've randomly selected that with a 4.0 is going to be a better student than the student with a 2.2. But not always. Okay, there's always some exceptions here. And that's essentially what numeric summaries do. We're taking a whole bunch of numbers, okay, an entire data set, and we are looking at one aspect of it, and we're trying to describe that one aspect with a single number. Okay, and so your GPA is kind of an average of your schooling. Okay, it doesn't tell you anything about your athletic ability or anything else about your life. Okay, we're just taking one aspect of your life, your academic portion, and we're summarizing it with a single number. Okay. Other numeric summaries, for example, we can also take someone and we can ask, what is your annual income? Okay, and it also tells you a little bit about the person, not a whole lot. You can boil. You're just using a single number, and essentially, when you meet a stranger for the first time and you're trying to make small talk, inevitably one of the questions is, oh, so what do you do? Okay. And what they're asking is, what do you do for a living? And whatever their response is, you are maybe this is maybe you don't do this, but a lot of times I feel like people are kind of creating kind of a judgment or a profile of you based on this one response. So if somebody says, oh, I'm a doctor, automatically you start thinking things, okay? If someone says, I'm a construction worker, you start thinking other things, okay? And, maybe that's fair or unfair, but basically, that's not a numeric summary, but it's basically just this one thing you're using to kind of create a profile of what this person's life might be like, okay? And that's what we do. With data, we have a whole bunch of numbers in our sample, right? Our sample represents a whole lot of people or different subjects, and we're going to try to summarize all of that data with a single number, and that's what we do with a numeric summary. It's very useful because we can compare one sample to another sample without having to look at individuals. Okay, that's why GPAs are useful. You can kind of compare one student to another student very quickly, without having to say, oh, he got an A in this class and a B in this class and an A in this class and a C in this class, et cetera, et cetera, et cetera. You can just say, oh, this student has a 3.5, this student has a 2.2 or 1.8. We're going to go with this student because he's got the better GPA, okay? It just allows for a very quick comparison, and that's what numeric summaries do. They allow for quick comparisons between samples of data, but we also have to realize that when you use a summary, you're cutting out a bunch of information. Okay, so I'm going to kind of just capture all of that in just a couple sentences here. Okay. Okay, so numeric summaries take the contents of a data set and try to summarize an aspect of it with a single number. Numeric summaries are very useful for making quick comparisons between different samples. Okay. but a numeric summary cannot capture all details of a data set. Okay, so an example. So I'll let you guys write that down. Okay, and so there are two broad categories of numeric summaries that we're going to cover today. Okay, so we have numeric summaries for center or central tendency, and we have numeric summaries for spread or dispersion. Okay. And again, remember that in all of this stuff, we're dealing with numeric data. Okay, so none of this, so if you're thinking of an example with categorical data, men and women, or whatever it might be, brown hair, black hair, blonde hair, these numeric summaries do not apply because this is only for numeric data. So keep that in mind. We've got numeric data going on. Okay, so we've got numeric summaries for center or central tendency, numeric summaries for spread or dispersion. Can you guys still hear me okay? Yeah. I'll hook this up, but it's kind of getting annoying to have to hold it in my hand here. Okay. Oh, you want me to go back? Shoot. That was my other class. Hang on. It was a good slide. For spread or dispersion also. Okay. There we go. We good? Okay. All right, so let's talk about the summaries, numeric summaries of center/central tendency. Okay. So when we talk about summaries for center and central tendency, I think we're talking about a numeric variable, and we want to get an idea of what numbers are typical values that appear in our data. Okay, so we're asking what are typical values appear in our data, okay? And essentially, is there a central number? Okay, so for example, we can talk about maybe the height of women in the United States. What's kind of a a typical value or a central value for the height of women in the US? And what would you guys say? Yeah, about 5'4"-ish. Okay, so if we were talking about the height of women, a value that we could use to describe the center would be 5'4", okay, or 64 inches. Okay, we want to talk about income in the United States. What's like a typical income in the U.S.? $50,000. Yeah, $50,000, something around there. Okay, give or take a few $1,000s. Okay, and yes, some people make more, some people make less, but kind of a typical income we can think of as around 50,000. Okay, and so any numeric variable that we can think of, we can generally come up with some kind of central number. And maybe we're unfamiliar with this, right? If I said, what's the, I don't know, mean cholesterol level in a person, maybe you don't know these numbers off the top of your head, and that's fine. But if somebody tells you what the central value is, that gives you a perspective of, oh, if somebody says, oh, we did, let's say you go to the doctor and they draw blood, okay, and they do some lab work, and they say, oh, your blah, blah, blah number is 352. And you're like, 352, I have no idea if that's good or bad, okay? And if they say, oh, the average number is around 350, you'd say, oh, okay, I don't seem too different from average, okay? On the other hand, if they say the average number is 5,000 and you're down at 352, oh my gosh, we got to hook you up to something, that might cause some alarm here, okay? And so if they say, so depending on what average or the central number is, you can kind of get a sense of whether something is strange or not, okay? So, so that's what measures of center and central tendency is. Is there a central number? Okay, so knowing the central values will allow us to know if a particular value larger or smaller than what is typical. Okay, and so we have two measures of central tendency or center, and one is the mean and the other is the median, okay? And so the mean is the balancing point of our data. The balance point of our data, and it takes into account extreme values that are large or small. Extremely large or small values. Okay, so the mean takes into account these extreme values, and sometimes that's what we want. Sometimes that's not what we want. Okay? The median, on the other hand, is the halfway point of our data. Half of the data is larger. Half of data is larger than the median. And half of the data is smaller. And the median is not affected by extreme values. Okay. The book says the median is preferred for skewed data, and that's because it's not affected by extreme values. But I would argue that sometimes even when you have skewed data, you do want your thing to be affected by extreme values, okay? So the mean and the median exist in both circumstances, okay? And the key difference, again, is the mean takes into account extremely large values or extremely small values. It's affected by extreme values. The median is not. And depending on your situation, maybe you want the mean, maybe you want the median. Or maybe it's useful to report both, okay? So let's get into this, okay? You guys have, I'm assuming, have seen the mean and the median before in your life, okay? And you know how to calculate these things. So I'll just very briefly cover calculating the mean and the median, but I'm assuming you guys are already familiar with it. The important thing is, when should we use the mean? When should we use the median? Okay, this is the important part, okay? So calculating, whoa, what's going on here? Okay, so calculating the mean. Okay, so symbolically, the symbol we use for mean is x bar. Okay, this is the symbol we use for the mean. And to get it, I'm going to just write the formula here. And this basically says, this means add up or sum. Okay, x is each data point. And then n is your sample size, how many data points you have. So basically it says add up all the data points, and it's in a fraction, right? Then divide by the sample size. Okay, so that's how you calculate the mean. Is this okay using this notation? We're adding up all of the x's, and then we divide by how many data points we have. Your sample size. You divide by n, the sample size. Okay, let's talk about finding the median. Okay, so again, the median is the spot where half of your data points are larger and half are smaller. Okay, so arrange values or data values from least to greatest, or smallest to largest. Okay, and cut your list in two. Cut your list in half. Okay, so basically n over 2 will be less, n over 2 will be greater. Okay, n over 2 of the data points will be less, n over 2 will be greater. Okay, so if n is even, the median will be between two numbers. Okay, and so you would take the average or take the mean of those two numbers. Okay, And if n is odd, the median will be one of the numbers in the list. Okay, so let's try an example here. Okay, so let's say we go to a restaurant and we ask people, what is your annual income? Okay, and so let's say the annual incomes in this restaurant are 45,000, 55,000. 59,000, 65,000, 70,000. Let's see, what else do I want to say? 90,000 and $11 million. Okay, so these are our annual incomes. Okay, so what is the mean annual income? X bar. So we'll take a minute to calculate these and then find the median annual income. Okay, and I've already done you a favor and I've already arranged them from least to greatest. Okay, so go ahead and take a minute here and solve these. Okay, if you're following along on YouTube, I'm going to just pause the video here so that there's not a whole lot of blank waiting time. Okay, so what do we find the mean annual income to be? We found it to be what? $1,626,285.71, right? Is that what we got? Something like that? Good. Okay, and the median would be what? 65,000, right? Because we have 7 numbers, n is equal to 7, and so 7 over 2 is 3.5. So we count and we go 1, 2, 3, and then so if we pick 65,000, we have 3 that are lower and 3 that are higher. Okay, so this is our median. Okay, and so what do you think? Somebody said, what's the typical income of these people? What would you say? What do you think you should say? Well, you'd probably want to say the typical income's around 65,000, but then there's a dude who makes 11 million a year. Okay, and but yeah, if you wanted to kind of get the typical income, yeah, you'd probably go with the median. However, if let's say these 7 people decided to go on some adventure journey together, and they wanted to take out life insurance policy, okay? I don't know. I don't think any company does this, but let's say there's some group life insurance policy, and we get some coverage for everybody. Okay, same amount of coverage for everybody. Do you think we should get coverage to replace $65,000 of income, or coverage to replace $1.6 million of income for each person?
65.
You think 65? So I would say, well, depending on the circumstance, I would say probably you want to get the $1.6 million of coverage for each person, just in case the person who makes $11 million dies on this adventure. You're not going to be completely in trouble. Okay, so you want to get. So depending on the situation, maybe you want to use the mean. In other situations, maybe the median is better. Okay, so you got to think about this. Do you want your answer to be affected by the extreme numbers or not? Okay. and different circumstances might change that. Okay, are there any questions? All right, just very quickly, what if I scribbled this number out? What happens to what is the median income now? So if I only have these 6 values, what's the median? So the median of the 6 lowest values would then be what? So I would pick, so now there's only 6 numbers, n equal to 6, and so here my median would be in between 59 and 65,000, where I have exactly three smaller and 3 larger, right? So my median would then be the average or the mean of 59 and 65,000. So I would add 59,000, oops, plus 65,000 and divide by 2, and I would get 62,000. So my median here is 62,000. Okay, so of the lower 6, 62. Is that clear? Okay, and so we can see the median is not really affected by these extreme values, and the only reason why it changed was because we actually removed a number. But we could see, you know, if we calculated the mean of these 6 numbers, it's going to be much smaller than 1.6 million. It would be, you know, around 60,000 in annual income. Okay, is that okay? Calculating the mean and the median. Okay, why do we bother calculating the mean and the median? What do these things tell us? They summarize the middle, the idea of center. Okay, they can either give us the balancing point, which is this, which one? Which one's the balancing point? The mean is the balancing point, and the halfway point is the median. Okay, so the mean and the median give us an idea of what typical values are or what central values are. The mean tells us the balance point. The median tells us the halfway point. Okay, and so when we take a bunch of numbers, we can boil it down to a single number that gives us kind of an idea of what the central values of this data set are. Any questions? All right, so let's cover the other topic, values of spread and dispersion. Okay. So again, let's say you go to the doctor and they take your blood and they say your blah 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 number is 245. Okay? And you go, "Oh, is that good or bad? I'm not familiar with blah 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 numbers." And you go, "Oh, 245." Okay, and then they say, "Oh, you know, lower is better. And the typical number is 200. Okay. Do you think you should be worried or not worried? Well, it's hard to say at this point because I have left out another key piece. We don't know the amount of spread. Okay. If I said the typical number is 200, lower is better. You're at 245. Now, if I say 99% of people, or if I say 95% of people are between 180 and 220, and you're at 245, then you'd go, oh shoot, I'm way high, right? But if I say, well, 95% of people are between 100 and 300, then maybe you don't have to worry so much, okay? So dispersion gives us an idea of, are most people in a small range of values, or is it like a big range of values? Okay, So if the typical number might be 200, and maybe the safe range goes from 100 to 300. That would be something with a large amount of spread or dispersion. Okay? But if the typical number is 200, and most people are between 180 and 220, then that would be something with smaller dispersion or smaller spread. So both sets of numbers there would have the same typical value, but the spread is different. And if your number is 240, you would be worried in the case where the spread is small, but you would not be worried if the spread is large. Okay? Does that concept make sense? Okay? So that's what we're getting at with spread and dispersion. Okay? So spread and dispersion describe whether the numbers in our data set have values that are close to each other, okay, that would be small spread, or have values that are significantly different. Okay, so I'll do my doctor example. So the, blah blah levels in blood. Okay. Your value is 240. The typical value is 200, okay? If the spread is small for blah blah numbers, we might say 95% of people are between 180 and 220, okay? In this case, 240 is a bit alarming. Okay. Okay. This is the number sign or hashtag. Okay. Does everything here make sense? I'll let you guys finish writing this down. So this gives us an idea of whether the numbers are close to each other, the values that we see in our data set are similar to one another, or if they're spread out. Okay? And so we have a few numbers that quantify this. Okay, so rather than saying this has small spread and this has big spread, we can actually give a number to this. Okay, and so comparing one data set to another data set, we can say this data set has less spread, this data set has more spread, this data set has a standard deviation of 3, this data set has a standard deviation of 12. Okay, and we can get an idea of how different the amounts of spread are. Okay, so we're just assigning numbers to spread, and that's what these numeric summaries are. So far, so good with this concept, everybody. Okay, so ways to measure spread. Whoops. Okay, we have the standard deviation. So maybe this is one of those words that you've heard before, but never really sure what it meant. So now you will know. The standard deviation, and then we also have the range, and we have the IQR, which is the interquartile range. Okay, so these are ways for us to measure spread. So all we're doing is we're taking that concept of, are the numbers spread out, are they close together, and we're assigning a number to it. Rather than just saying lots of spread, little spread, we're going to say standard deviation 25, standard deviation 2. Okay, we're putting numbers to these things. That's what we're doing. Okay, so the standard deviation is just one way for us to assign a number to this concept of spread. Okay, the symbol for standard deviation is S. Okay, and it's just one way to assign a number to spread. And we can think of it as, this is a very loose definition and it's not exactly this, but we can think of it as we're going to take the mean, the balance point of our data, and we're going to measure how far each data point is from the mean. Okay? So if the mean is 200 and almost all of our data points are very close to the mean, like 190 and maybe the farthest one's like 180, we measure how far those are away from the mean, and we kind of come up with an average number of the distance from the mean. Okay? So the standard deviation, we can think of it as the average, and it's not exactly the average, so I'm going to put this in quotes, the average distance points are from the mean. Okay, so we have data points, and we're talking about the average distance that they are from the mean. Okay, so let's just do 2 simple examples here. Okay, so let's say we have 2 families, and they each have 5 kids. Okay, so we've got I don't know, the Baker family, and we have the Jones family. They each have 5 kids. All right, so let's say in the Baker family, the kids are 8, 9, 10, 11, 12. Okay, and in the Jones family, so in both families, I will say that the average age is 10, but I'm going to do it like this, 14, and over here, 6. Okay. So in the Baker family, the kids are 8, 9, 10, 11, 12. And in the Jones family, the kids are aged 2, 6, 10, 14, and 18. Okay? So just picture these two families. You can already have an idea of what life is like in each of these homes, right? So this is so obvious, but which family has more spread? The Jones family, right? The oldest kid is 18, the youngest kid is 2, and you can kind of see everyone all spread out, and the ages are very different, and they're having to deal with kids going to college and also kids in diapers at the same time, okay? And the Baker family is just like boom, 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 boom. All the kids are popping out, and and there's not, all the kids are kind of in diapers at the same time, and they're all going through, stuff like that, okay? Well, anytime you have 5 kids, there's going to be some spread, but we can imagine the difference here, okay? So when we calculate the standard deviation, how will the standard deviation for the Jones family compare to the Baker family? The standard deviation over here is going to be big. Standard deviation here is going to be smaller, okay? Because the standard deviation is just a way to quantify the amount of spread, okay? So what is the average age in the Baker family? Average age is what? 10, right? So average, let me write mean age. The mean age is 10. Okay, so in both families, the mean age, and you can do this yourself, you can add them all up and divide by 5. The mean age is 10, and over here, the mean age is also 10. Okay? So I do 8, 8 plus 9 plus 10 plus 11 plus 12, divide by 5, and I get the mean age to be 10. Okay? All right. So if the mean age is 10, let's look at each of these numbers, and we ask how, let me rewrite these numbers down here. We're going to ask how far is each age from the mean? So I have 8, 9, 10, 11, and 12. So to get how far are they from the mean, what do I do? I'm basically just going to subtract each number from 10, or 10 from each number. So how far is 8 from 10? It's 2 years away. How far is 9 from 10? 1. How far is 10 from 10? 0. 11 from 10? 1. And 12 from 10? 2. Okay? And I said average in quotes because we do some things to make our lives complicated. We're going to square them, then we divide, then we take kind of the mean, and then we're going to take the square root, okay? So it's like we're going to square them, and then we take the mean, but not really, and then we're square rooting that number, okay? It's just, we're just complicating our lives a little bit, but this is the rule, this is the method that the smart statisticians have decided is the method to follow, okay? So this is what we're going to do, okay? And I'll write all the steps out, okay? So we ask how far is each age from the mean, and then the next steps will be square these values. So what is 2 squared?
4.
2 squared is 4. What is 1 squared? 1. 0 squared? 0. 1 squared? 1. And 2 squared is 4. Okay, so we square each of these values. Okay, and then we're going to take the mean. So to take the mean, we add them up and we divide by how many numbers we have, right? But again, we make our lives complicated, so we're going to add them up but divide by one number less. Okay? And I'll write all of this down, okay? But we're going to add them up and divide not by 5, but divide by what? 4. Okay, so we add them up and divide by 4. Okay? Add up and divide by n minus 1. Okay, so I do 4 plus 1 plus 0 plus 1 plus 4, and I get 10. But then I do 10 divided by 4, and I get 2.5. Is this okay with everybody so far? Okay. And then lastly, to undo the fact that we squared them, we're going to take the square root. Okay, so we take the square root of 2.5, and I get like 1.298 or something. 1.581. .5811. Okay, so the standard deviation of the Baker family is equal to 1.5811. Yes.
Sorry, why did we divide by 4?
That's just the rule. I'll put, okay, so let me, huh?
Where did we get 4?
So normally if I said take the average of these numbers 4, 1, 0, 1, 4, you would add them up and divide by 5, right?
Right.
Okay. But for whatever, well, the reason is called Bessel's correction, but there's a reason, and we don't divide by 5, but we choose to divide by 4 instead. Okay, so we take whatever number we would normally divide by to get the average, but we actually divide by n minus 1. Okay, so it's like taking the average where you add them up and you divide by how many you have, but you're using n minus 1 rather than n itself. Okay, so let me just list off the steps on the next page. I'll also write out the formula, and then we'll work through finding the standard deviation for the Jones family. Oh, actually, we might run out of time. So I might have to move on to the next topic here, okay? But, so we won't do the Jones family together as a class. I'll still write out all of the stuff for the standard deviation, but we might run out of time here, okay? So just because, okay. So the formula for standard deviation, and if you don't like formulas, you don't have to use this, okay? I'm going to put this up here, and it looks scarier than it actually is. Okay, so this is the formula, but let me just tell you the steps, okay? Steps for finding standard deviation. Okay, number 1, find the mean. Okay, and again, think of the standard deviation as quote-unquote average, not really, average distance points are from the mean. But it's not really the average, okay? Find the mean. Find the distance from the mean. Distance, each point is from the mean. Okay. Square those distances. Okay. Add them up. So this part is like finding the mean, but or average. Add them up. Divide that by n minus 1. Okay? And then take the square root. So, you know, we had 2, 6, 10, 14, 18. Okay, so the mean is equal to 10. So distance from the mean would be 84048, and squared distance 64, 16, 0, 1664. summed. So here I will list off each step. Step 1, step 2, step 3, step 4 would be 64 plus 16 plus 0. Okay, and so the standard deviation of the Jones family is 6.3246. Okay, we got to keep going here. So, I know some of you guys are still writing. I'll post some of these pages up online. Okay. So if you guys are still writing, you can take a look at the notes that I'm going to post online. Okay, so this is useful because once we have the standard deviation, we can then talk about z-scores. Okay, and z-scores is the distance we are from the mean, but not just the raw distance, but the distance expressed in standard deviations. Okay, so z-score is the distance a point is from a mean, is from the mean, expressed in standard deviations. Okay, so I could say it's Michelle, right? So Michelle is, let's say, 36 inches away from me. Okay, now I could say she's 36 inches away from me, but I could say express that in feet, and you would take 36 and you divide by 12, and you'd say she is 3 feet away from me. Okay, and so we're doing the same thing. We're taking a distance, except we're expressing it in standard deviations. So basically, a z-score is equal to whatever data point you're looking at, and you take that distance from the mean. So you take the distance something is from the mean, x minus x bar. This is the distance from the mean, and then you're going to divide by s to get it in standard deviations. Okay? So for the Baker family, okay, x bar, the mean age is 10 years old. Okay? And the youngest is 8. Okay, so his z-score is equal to 8 minus 10 divided by the standard deviation, which I think we said was 1.58 something, 5811. Okay, so we get -2 on the top. He is 2 years younger than the average, divided by 1.5811. So 2 divided by this. So he is 1.265 standard deviations below the mean. Okay. Yes.
Did you get that number in the denominator?
This comes from the previous page when we found the standard deviation for the Baker family,
Okay.
or whichever family had the kids all close together. I think it was the Baker family. Okay? Okay. You're going to have some exercises in your homework covering this. I want to talk about the range and the IQR, so don't pack up your things yet. The range and the IQR, I think, are simple enough concepts that you can read the homework and watch my videos and figure it out. But I just want to talk about them here to get you guys set up, okay? So anyway, what the Z-scores is, it also allows you to compare like apples to oranges. We can talk about which is more unusual, a man who's 7 feet tall or a woman who is 6'5". Okay, we would say in both cases they're both very, very tall, but which one's more unusual? The man who's 7 feet tall or the woman who is 6'5", okay? And you would calculate a z-score, okay? And you'd get the z-score for the man who's 7 feet tall, and you'd say, oh wow, he's this many standard deviations away from the mean. And you'd find the standard z-score for the woman. And whichever one has a larger z-score, that's the one that's more unusual, okay? That's also going to be covered in the practice quiz as well. So let's talk about range and IQR. Okay, so for range, the range is the largest data point minus the smallest data point. It's just the distance between the largest value and the smallest value. Max minus min, okay, or just distance between the two extremes. Okay, so for the Baker family, the oldest kid was 12. Oldest kid was 12, and the youngest kid was 8, which gives us a range of 4 years. For the Jones family, the oldest kid was 18, and the youngest kid was 2. Okay, so that gives us a range of 16. And that's range. Okay. IQR, interquartile range, is the distance between the 25th percentile and the 75th percentile. Okay. Are you guys familiar with the terms percentiles? I'm hoping. Okay. So to be in the 25th percentile, what does that mean? That means 25% of people have values that are smaller than whatever score it is that we're looking at. To be in the 75th percentile, it means 75% of people have values that are smaller than yours. Okay? The 50th percentile means 50% of the data is smaller than yours. What's another name for the 50th percentile? Median. The median. Okay? So the IQR is basically the 25th percentile, which we call Q1, or the first quartile, and the 75th percentile is the third quartile, or Q3. And the IQR is equal to Q3 minus Q1. So how do we find Q3 and Q1? Okay, well, essentially we want to divide our data into quarters. So what we do is we first take our list of data, arranged from smallest to largest, and we find the median. And that cuts our data in half. And essentially, now that I've got half the list, I'm going to just cut that list in half again. And now I have quarters. And I do that to the other side. I find the median, it cuts it in half, and then I cut that list in half again. Okay? So essentially, you're going to find the median, cut the list in half, and then once you've cut the list in half, find the median again to cut those lists each into quarters. Okay? So to find quartiles, okay, first find the median. Okay, and cut the list in half. Cut the list into two. Okay, then take each half and cut those in half again. Okay, and the smaller one is Q1. Okay, the halfway point of each half. So the quarter of the smaller one is Q1. The smaller is Q1, and the halfway of the larger one is Q3. Okay, question.
Why would you do that?
To find the quartiles, but why? Okay, so these are just different ways to assign a number to this concept of spread, right? So spread is just like, are the numbers far apart or are they closer together? And you know, the mean and the median, they're just ways to describe center. And we have 3 ways to describe spread, and they all kind of emphasize a different aspect. The IQR tells us where the difference between the 75th percentile and 25th percentile. And it's useful in certain situations, okay? And so we do this as just another way of kind of explaining the spread of our data, okay? So, you know, somebody might say, you know, to get into UCLA, the average GPA of the student admitted was, I don't know, a 3.8 or something like that. Okay, I have no idea. I'm just making this number up. Okay, and then you say, well, okay, what's the IQR? Okay, and the IQR is the difference between the lowest 25th percentile. Okay, so kind of like the lower performing ones, and then the upper performing. And you say, oh, there's an IQR of 0.3. Okay, meaning the difference between the top 25th percentile, the 75th percentile GPA, and the 25th percentile GPA, there's only a difference of 0.3. Okay, and so that gives you an idea that there's kind of a tight race. Okay, whereas the range, maybe they admitted someone with a very low GPA, but on exceptional circumstances. So the range might be very large, but the IQR might be a lot smaller, kind of giving you a better representative picture, because the range is affected by people at the extreme ends. The IQR is not. Okay, like the mean is affected by extreme values, the range is affected by extreme values, and the standard deviation is also affected by extreme values. The median is not affected by extreme values, the IQR is not affected by extreme values. Okay? All right, so do your homework, work through the problems that I've assigned and also on the practice quiz, and I hope you can prepare adequately for next week's quiz. So we'll see you guys next week.